Okay, so here's a summary of everything that'll be on the quiz. Um, for the most part, we're dealing with like proportions and percents, either finding the proportion or percent in between of two values, or maybe greater than a value or less than a value, or you're given the percent somehow, given the proportion, and finding the value or the mean or the standard deviation. Um, okay, but most important thing is that we're dealing with density curves. So you have these density curves, and density curves are these curves that could be uniform, they could be bell-shaped, kind of. Those are the normal distributions or normal curves. Most important thing is that the area under the curve is the total area. That's what they say up here. Is one. So, and 1 is like 100%. And so, most important thing probably for this lesson is understanding that that area for us, when we're doing problems, that area has meaning to it. And the meaning of it is it's the proportion or percent, it's the same thing. So that area is either the proportion or percent, that's greater than some value or less than some value, or between two values. And these are values in the distribution. So if the values in the distribution are heights, then you might be finding the area between two heights. And that area is the proportion of the data that's between those two heights. The proportion of the people, if you're talking about the heights of people, whatever the area is, that's the percentage of people that are between two heights, or greater than a height or less than a height. So I think that's the most important thing to see, is that area for us gets interpreted as proportion or percent of all the data that's in the distribution. So, yeah, and then the other thing is making sure you know this formula, right? We use this formula a lot in different ways. And then table A. I'm going to do a lot of table A. I'm going to do table A and the calculator for every problem that you can. I'm going to do both ways, just so you can see how it's done, and you can choose whichever way you want. Okay. Okay, so 41, they say Sally takes the same bus um, to work every morning. The amount of time and minutes that she has to wait for the bus can be modeled by a uniform distribution on the interval from 0 to 10 minutes. Okay, so first they want us to draw a density curve to model the amount of time that Sally has to wait for the bus. Be sure to include scales on both axes. Alright, so kind of you can see kind of how they did it down below. A lot of times they'll do just a little density curve, like this. And they'll put this as, that'll be the 0 on the, or we'll do a separate one, the 0 for the x and y. And then this will go to 10. Right, the values are the minutes on the x-axis. And then there's just some kind of uniform distribution, so it'll look something like this, like a rectangle. Okay, so really this is the uniform distribution here. I think the most important thing is seeing, since these areas of density curves have to be 1, you can see this, we can use geometry sometimes. So this area of this rectangle has to equal 1. So if you think about it, if this side is 10, then this side has to be 1/10, so that they multiply to be 1, length times width. Okay, and just know whatever length, these uniform distributions are always rectangles. Whatever this length is here, just the height is just going to be the reciprocal. So if this length was 5, this will be 1/5. If this length was 3/2, this height would be 2/3. Okay, so that's just drawing a density curve. We label both axes, and we could even label it like with, this is minutes. Okay, actually, let me put it down here a little bit. Okay, so they say, for B, they say, on about what percent of days does Sally wait between 2.5 and 5.3 minutes for the bus? Okay, so, so this is, right there is, let's say 2.5, and let's say 5.3 is about right there as far as minutes. So we want to find all this area going to the top of the distribution, and we want to find all this area here, which in that is also a rectangle. Okay, so now think about if this is a rectangle, I'll kind of put it over to the side here. That's that rectangle that's in the middle. So think about it, if this goes from 2.5 to 5.3, then this length you can get just by subtracting. So, and that's true, just anytime you want a distance along an axis, say the x-axis, just subtract the x coordinates that length goes to and from. So if you do 5.3 minus 2.5, that's 2.8. And we know that it's a uniform distribution, so the height's always the same, so the height's 1/10. And then they say, what percent of the days does Sally wait between 2.5 and 5.3 minutes for the bus? So the percent is whatever this area is. So if you do 2.8 times 1/10, that ends up being 2.8 times 1/10. That's 0.28. Okay, so that's really 28% of the time Sally waits for the bus between 2.5 and 5.3 minutes. Okay, then they say find the 70th percentile of Sally's wait times. Okay, so I'll draw like another one real quick. And they want the 70th percentile, so they want this number here, whatever that number is. If it's the 70th percentile, so remember how percentiles work is always it's the percent that's less than or equal to. So that means 70% is less than or equal to x, which is all that area. Okay, so we know that if we can set up a little equation, so then we know that this height times this length here, this height here times this length has to equal 0.7, has to equal this area. So you can just do a little algebra, just 1/10 x equals 0.7, and then times both sides by 10, and you get x equals 7. Okay. So find the 70th percentile of Sally's wait times, so that'll be 7. Okay, so those are the answers to B and C. Okay, next one. Let me zoom in. Okay, an internet reaction time test asks subjects to click their mouse button as soon as the light flashes on the screen. Okay, the light is programmed to go on at a randomly selected time after the subject clicks start. The density curve models the amount of time the subject has to wait for the light to flash. Okay, so they say first time, what height must the density curve have, and justify your answer. Okay, so this area has to be 1, and it's a rectangle. So that means when we do, length times height, that has to be 1. We know that since this length is 4, right, just 5 minus 1, and this height has to be 1/4. So this height up here is 1/4. Okay, and the answer, if you're justifying, because the area must equal 1. And that's, yeah, so if the height's 1/4, then the area of that rectangle will equal 1. Okay, part B. About what percent of the time will the light flash more than 3.75 seconds after the subject clicks start? Okay, the fact that they want percent means they want area, right? Anytime they ask for percent or proportion, they really want area. And they say what percent of the time will the light flash more than 3.75? So let's say that's 3.75 there. And they say more than. What percent of the time will the light flash more than? So more than is 3.5 or greater seconds. So that's all that area there. So we just find the area of that rectangle. And that's this base here. This length here is 1.25. Just do 5 minus 3.75. That's 1.25. And then times that by 4. So 1.25, or times by 1/4, sorry. Times 1/4. Let me get a calculator. 1.25. And that's 0.3125. Okay, that could be the answer. They specifically asked for a percent. And so maybe we'll just write it as a percent. Okay, last one, they say, calculate and interpret the 38th percentile of this distribution. Okay. All right, let's erase that. Okay, now if they want the 38th percentile, they want to make it so that there's some point, let's just say 38% is about a third, right? So maybe a third would be like maybe around here somewhere. That would be like a third of the area. So I'm just going to put down here, we don't know the value yet. Okay, but the 38th percentile is some point on here, some value, where the area less than that in this distribution is 0.38. So if we draw this rectangle, we want all this area here to equal 0.38. Okay, so here we'll do a little equation. So notice this is a rectangle again. So remember, just like the other rectangles, when we had numbers, to find this base, we just did the x value at one endpoint minus the x value at another endpoint along this distance. And we'll do the same thing, even though this is an unknown value that we're calling x. Just do x minus 1, and that's this distance. For whatever x value you have, this distance is x minus 1. Okay, so that's this width times the height, and that'll be the area, and we want that area to be 0.38 in order for that value to be at the 38th percentile. Okay, and then we can do different things. I'll times both sides by 4 to get rid of the 1/4. We'll times both sides by 4, just algebra. That'll cancel out the 4's on the left. Okay, 0.38 times 4 is 1.52. And then add both sides, add 1 to both sides, and you get 2.52. Okay, so that makes sense. That looks like that's actually kind of where we estimated here, 2.52, and then that's about 38%, that area to the left. Okay, so the next one, number 47, they say the weights of 9-ounce bags of a particular brand of potato chips can be modeled by a normal distribution with mean 9.12 ounces and standard deviation 0.05 ounces. Sketch the normal density curve, label the mean and the points that are 1, 2, and 3 standard deviations from the mean. Okay, so that's all we're doing. I'll kind of make this big. So we have enough room to label. So it doesn't have to be perfect, but just some kind of bell curve. Okay, right in the middle. For a normal curve, the middle value is the mean, median, and mode. But for us, we're concentrating on the fact that it's the mean. And then, if we want to say one standard deviation, it's got to be 34% of the area. So maybe right there. And then whatever distance this is, the next line has to be the same distance. Just try to get as close as you can. So maybe something like that. That might be a little thin. And then just the same distance, that'll be 3 standard deviations above the mean. Okay, same thing, whatever this distance is, we'll go the same distance in the other direction. So maybe right there somewhere. Okay, the next one, maybe right there. And then right there, let's say. Okay, so the middle value is the mean, 9.12. And then if you want to go, this will be 1 standard deviation more than the mean. Since standard deviations are 0.05, just add 0.05 to this, and that'll get you the next value. And then, this is 2 standard deviations. 2 standard deviations is 0.1. 0.05 times 2. 0.1 plus 9.125 is 9.12 is 9.22. And really all we're doing is adding 0.05 to the previous value. And then going the other way, we'll subtract 0.05. So subtract 0.05, 9.07, subtract 0.05, and subtract 0.05. Okay, and then the way we label it, n, so this is a normal distribution, and then just put the mean, comma, the standard deviation. And that's how you label each normal curve. Okay, for the next problem, they talk about using the empirical rule for the following question. So let's fill this in just for practice, and then we'll be able to use this drawing here to answer those questions. So in the first 2 sections, that are within 1 standard deviation, more or less than the mean, each of these is 34% according to the, roughly, according to the empirical rule. Okay, the next outer sections between 1 and 2 standard deviations from the mean will be 13.5% on either side. This is symmetric. Okay, the next section will be 2.35%. Okay, and then all this section to the left and to the right forever, all together is 0.15%. So pretty small. So when you get outside of 3 standard deviations, there's very little of the data. If your data follows a normal distribution, very little of the data is outside of 3 standard deviations from the mean. So, all right, so let's use this for the problems down below. Okay, so they say about what percent of bags weigh less than 9.02 ounces. Okay, here's 9.02, so less than that is just adding up all the percents in the empirical rule. So 2.35 plus 0.15 plus 0.15 is 2.5%. Okay, they say for B, they say a bag weighs 9.07 ounces, or a bag that weighs 9.07 ounces is about what percentile in this distribution? Okay, so a percentile is the values in the distribution that are, the percent of the distribution that's less than or equal to that value. Okay, so if you find 9.07, the percent that's less than or equal to is just all of this area added together. So we know that this is 2.5, and then just add 13.5, and so that'll be 16%. Okay, and that's it. Okay, next one. So now we'll do calculators. We use a calculator for a lot of these. Okay, the next one they say still refer to exercise 47. So here I'll write down, what was the mean and standard deviation? 9.12 and 0.05. Okay, for the next questions they say, about what percent of 9-ounce bags of this brand of potato chips weigh less than the advertised 9 ounces? Okay, so let's do that first. Let's say, first off, they want a percent. If we're doing a calculator, so here, let's write this. If we're using a calculator, if they want a percent or a proportion, we always do normal CDF in the calculator. Okay, so when we do normal CDF, so here, let's take this calculator. Okay, so when you do normal CDF, do second, and then VARS, which is distribution. It's the second thing. Okay. So we want they said what percent is less than, percent is less than 9 ounces. So actually, let's draw this first. I should do this first. So when we draw this little normal distribution here, just a quick drawing, put the mean. Okay, they want the percent of potato chips that are less than 9 ounces. So let's say 9 is right here. Say 9 ounces is right here. So the percent less should be pretty small. You know, it's about a little over 2 standard deviations away from the mean, or less, and so it should be a pretty small percent. But notice that we're going to the left forever, so there is no lower. You know, when they say lower value, there is no lower value because this goes on forever. So just pick a big lower value. A lot of times the calculator defaults to -1 e to the 99, so that's just a huge negative number. That's -1 times 10 to the 99th. So that's some huge negative number. So put that for the lower, and then the upper is our value, 9. And then we'll put the mean and standard deviation of this distribution in there. Okay, click down and then hit paste. It'll paste it into a blank screen, and then just hit enter one more time, and then that gives you the answer. So, and that's kind of what we expected, a pretty small percentage. So really 0.00819 is really 0.81, let's just say 0.82%. Okay, so less than 1% of the bags weigh less than 9 ounces. Okay, so let's do the same thing, but with table A. So you have options, and sometimes they'll just ask questions just about table A. So you have to get the exact value that table A gives you, so that so that when you answer the question, you show that you can use table A. Okay, so same thing. We're still finding the same value, but table A needs it. Table A only has z-scores and then percents and proportions in the inside. So here we have to find the z-score that's associated with our value 9. So let's do that first. So we'll use the formula z equals value minus mean. So let me do it this way. Value minus mean over standard deviation. For us, the value is 9. That's the mean. Standard deviation. Okay, so this is negative 0.12 over 0.05. That's negative 2.4. Okay, so this is our z-score that's associated with the value 9. Okay, so first we'll look at 2.4 and our z-score. So find 2.4 here, and it's 2.40. So really it's 2.4, so it's this value here that we're looking at. 2.4, yeah. Okay, and notice that's so this is the percent that's less, the area that's less than that value, and that's what we wanted. That weighs less than. That was in the problem, less than. And that's what these give you. Naturally, they give you less than. If they want greater than, that's when you have to do the 1 minus or 100 minus 100, the percent. But in this case, this is the answer. And notice, this is the exact same answer that we got from the calculator. That won't always be the case. Sometimes these will be a little off. But you can see we got the exact same value in this case. Okay, and then the last problem they say, is this likely to pose a problem for the company that produces these chips? I don't know. I guess I would say no, because that's a small percentage, but I don't know. Maybe if you deal in volume, maybe a small percentage means a lot of money lost. If people get upset that I don't know, that there's not that much chips in their bag. I don't know. But probably not that big a deal. Okay, next one is kind of more of a conceptual question, or just kind of testing you on your understanding of just a single concept. When you are looking at the shape of a distribution, how can you tell from the shape what's bigger between the mean and the median? Okay, so they say the figure displays two density curves that model different distributions of quantitative data. Identify the location of the mean and median by letter for each graph and justify your answer. Okay, the first one's skewed right, since most of the data is to the left. And when you have skewed right, so first off, this biggest value is the mode. They don't ask for that, but that biggest value is the mode. Same thing in the other one. This is bimodal. So these are the mode, these tallest values. So in this one, A would be the mode, the one that happens most frequently. And this one, A and C, would each be the mode, because those happen the most frequently, and looks like about the same in that other distribution. Okay, for skewed right data, remember this is the tail here, and the mean is further along the tail. And so this value C, over here, C would be the mean, and then B would be the median. Okay, so you can see that in this case, the mean is greater than the median. Okay, and that's because C on this x-axis, C is just a greater value than B since it's further to the right. Okay. In this one, this is symmetric. It doesn't matter what kind of symmetry you have, whether you have like a normal curve, a uniform curve, or a bimodal curve like this. If the curve is symmetric, then the mean and the median will be that same middle value. So B is the mean and the median, and so they'll be equal in this case. And that's true for any symmetric, we can say, because this distribution is symmetric. Okay, and the other one, it's because the distribution is skewed right. Okay, next one. So here they give us a normal curve and they say estimate the mean and standard deviation of the normal density curve below. Okay, so the mean will be, whatever this middle value is. Looks like maybe 10, but just whatever from the top. If you have a normal distribution, that's definitely the mode, but that'll also be the mean and the median. Okay, so it looks like the mean is about 10. And they say estimate the standard deviation. So standard deviation will be some point here, somewhere around here. So that 34% of this, if you think about all this area, you need about a third of all this area to be in between the mean and whatever the next value is here. So it looks like, I don't know, somewhere between 12 and 13. I would say like maybe, I don't know, maybe right here, 12.2. That looks like that's about 34% maybe here. So I would say, yeah, maybe 12.2. Or sorry, 2.2. Yeah, so this point is 12.2, but this distance would be the standard deviation. So I would say about 2.2. Something like that. Mean, and that's the standard deviation. All right, so something like that. I think everyone should get the mean is 10, maybe exactly 10, and the standard deviation somewhere around 2. Okay, for 55. A study investigated about 3,000 meals ordered from Chipotle restaurants using the online site Grubhub. Researchers calculated the sodium content in milligrams for each order based on Chipotle's published nutrition information. Okay, the distribution of sodium content is approximately normal, with mean 2,000 milligrams and standard deviation 500 milligrams. Okay, about what percent of the meals ordered exceeded the recommended daily allowance of 2,400 milligrams of sodium? Okay, so here let's write that for this one. So the mean for this distribution was 2,000 milligrams, and the standard deviation was 500. Okay, they asked for what percent of the meals exceeded the recommended daily allowance of 2,400. So let's write a little normal curve. Okay, here's the mean, 2,000. We want to know the percent that exceeded 2,400. So let's say right there is 2,400. So we want that area right there. Okay, so we'll do it both. I'll do it both in the calculator and using table A. Okay, so first thing in the calculator. So remember, anytime you want percent or proportion, like in this case, normal CDF. Okay, so our lower in this case is 2,400. So put that in there. And then the upper, just pick something really big relative to the mean and standard deviation. So just put a bunch of ones in there, basically. Okay, and then we'll put the mean was 2,000, and then the standard deviation was 500. I'm going to hit enter. Okay, so remember that when you do normal CDF, it gives you it gives you the percent or proportion. That's to the left or right. So that's what that's giving us. So this is the percent. So we'll say 21. Whoops. 21 point. Let's say 19%. Okay, so that's about, they say about what percent of the meals exceeded the recommended daily allowance of 2,400, and so that's about 21% of the meals. Okay, so let's do the same thing with table A. Okay, in order to do table A, we have to find z-scores. So we'll do the z-score formula first. Okay, so the particular value was 2,400. The mean was 2,000. And the standard deviation was 500. Okay, the top will be 400 divided by 500, and that's 0.8. So our z-score is 0.8. So we'll go over and to find the z-score of 0.8. Let's highlight that. Okay, so 0.8, it's 0.80, so that'll be the set point 7881. Okay, but remember, all of these values is the percent less than, right? So like if we shaded all of this area would be 0.7881 or 78.81%. But we want to find the area that's greater than our value, so we'll do 1 minus that. And just to see, just make sure people know, you could either do 1 minus the proportion, .2119, and then turn that into a percent. Right, notice we get the exact same thing that we got from normal CDF. Or you can turn this 0.7881, you can turn that into a percent, 78.81%, and then do 100 minus that. Okay, and either way you get the same percent. So okay, so it got same exact value. That won't always happen, remember, that they're exactly the same like that. Okay, next one. Watch the salt. Refer to exercise 55. So previous exercise, we're using the same mean and standard deviation. And they say about what percent of the meals ordered contain between 1,200 milligrams and 1,800 milligrams of sodium. Okay, so we'll do normal distribution. So our mean, what was it, 2,000? Yeah. Our mean is 2,000. Okay, and then we want between 1,200 and 1,800. So that's 1,200. So that's 1,800. So we want all that area. Okay, so that's just kind of area in between. So normal, when we do normal CDF, 1,200 will be our lower, and 1,800 will be our upper. Okay, same mean and standard deviations before. Hit enter, and that's it. Oops. Okay, so they say about what percent of meals contain between 1,200 and 1,800 milligrams. So about 28.98%. Okay, so let's say we're doing the table A way. So let's find z-scores. So if whenever you're finding the percent in between two values, you'll have to find z-scores for each value. So we'll do that for each one. Okay, so the z-score for 1,200 is 1,200 minus 2,000 divided by 500. Okay, and then we'll find the z-score for the 1,800. Okay, and then for each of these, we'll go to table A. Okay, so for the negative 1.6 z-score, so we'll find negative 1.6 and it's negative 1.60. So we're looking at that value there. And then for the negative 0.4, then it's this for negative 0.40. So it's that value there. Okay, and all we do is subtract those two values. Just do the bigger minus the smaller. So we'll do the 0.3446 minus 0.0548. Okay, let me do that in my calculator. 0.3446 minus 48. And that ends up being 0.2898. So 28.98%. Okay, is that what we got before? Yes, that's exactly the same. Okay, so far they've been exactly the same, doing normal CDF or using table A. Okay, last one. So now they're talking about a standard normal area. So find the proportion of observations in a standard normal distribution that satisfies each of the following statements. Okay, so when they talk about a standard normal distribution, so that's a normal distribution where instead of using like actual values in context, like in the last one, these values here were like milligrams of sodium. So instead of using like actual values from some context, they'll just put z scores in the bottom and just z scores. Okay, and that's called a standard. They call that a standard normal distribution. Okay, so now if we do, so in a standard normal distribution, the mean is always 0 and the standard deviation is always 1. Okay, so notice the first one is talking about we want the proportion that has z-scores greater than negative 1.66. We'll draw our graph. Okay, this is going to be 0 because in a standard normal distribution, the mean is always 0. And then we're looking at negative 1.66. And we want the percent that's greater. So we want all of this percent greater. Okay, so it should be pretty big. I don't know, maybe 80 or probably 90%, somewhere around there, 80 or 90%. So let's see once we go to the calculator. Oops. Okay, so second bars, distribution, number 2. It's normal CDF. So yes, now our lower is the 1.66. Our upper, we'll just keep that, just some big upper number. Doesn't matter. Yeah, we could do 1111 or something. I could have kept that other number there too. We'll get the same answer. Yeah, and then 0 and 1 for our mean and standard deviation. Paste. Okay, oh, that was a little bit bigger than I thought. Okay, 95%. Okay, so this first one is 90, whoops, say 95.15%. Okay, and then part B, so we'll do the same thing. Oops. Okay, second vars. Okay, keep that same lower, but because we want to go in between that and 2.85. So we'll just do 2.85 for our upper. enter. Okay, so not much different. Okay, and actually I should have drawn a graph for that one. So that draw the graph for that one. Oops. Okay, so that's the area that we were finding. That's the percent that we were finding. Okay, and that was 94.94%. Okay, so let's do the same thing with table A now. So nice thing about this one is we don't have to find z-scores. We're given the z-scores. So the first z-score is negative 1.66. So let's find that. So negative 1.66. Okay, so here's negative 1.6 here, and then here's 0.06 up here. So it's really like this value here. That one there. Yeah, just to see clearly, it's these two values here. Okay, so negative 1.66. That's our value. Okay, and then keep in mind all these values in here are area to the left, but if we want to find area to the right, like we did for the first one, then we have to subtract from 1 or subtract from 100. So we'll do, so this value, oops, we'll do 1 minus 0.0485, 0.9. 515. It's 95.15%. That close? Yeah, it's exactly the same again. It's not usually exactly the same like that. Okay, and then actually maybe it's exactly the same because our z-scores aren't rounded. They're exactly to the tenths or to the thousandths, so I guess that makes sense. Okay. So, and then the part B says for part A. If we want to do part B, then we have to look at the other z-score, 2.85. So let's find that one. Okay, there's 2.8 there, and 2.8, there's 0.05, so we're looking at that number there. Okay, so one second. Okay. So we will subtract these two values, and that'll be the percent in between. Just do 0.9978 minus 0.85. So I'm doing this in my calculator, and it's 0.9493, 94.93%. Okay, and that's basically we got 93.94% if it's rounded. Okay, next one, Sudoku. Mrs. Starnes enjoys doing Sudoku puzzles. The time she takes to complete an easy puzzle can be modeled by a normal distribution with a mean of 5.3 minutes and a standard deviation of 0.9 minutes. Okay, what proportion of the times does Mrs. Starnes finish an easy Sudoku puzzle in less than 3 minutes? Okay, so we'll just do a little simple here. So her mean is 5.3. Okay, standard deviation is 0.9. So less than 3 is going to be pretty far out. So we want that. And I want all this area to the left, less than 3. So it should be a pretty small percentage, I think. Okay, so let's do that in the calculator first. So second bars, when we went percent or proportion, that's normal CDF. Okay, lower is just some really big negative number, or keep that. The upper's 3. And we'll put in our mean as 5.3 and standard deviation is 0.9. Okay, so yeah, pretty small. Okay, so that's 0.0053, so 0.53%. Okay, so it's pretty rare that she finishes a Sudoku puzzle in less than 3 minutes. Okay, next one, we'll do all these in the calculator first, and then go back and do them all in Table A. Okay, so how often does it take Mrs. Starnes to do? How long does it take her more, or how often does it take Mrs. Starnes more than 6 minutes to complete an easy puzzle? Okay, got this. Okay, there's 5.3. And then more than 6, so it'll be around there, 6. And that's what we're looking for right there. Okay, so now 6 is going to be our lower, and our upper is just going to be a big positive number. Okay, so let's do that in the calculator. So I guess, I don't know, maybe 40% of the time. Something like that. Oh wait, maybe less actually. Maybe 25%. Yeah, so just do 6, and then some big positive number, 1111 is good for this one. Okay, got the same mean and standard deviation as before. Okay, oh, whoops. Yeah, so here, let's paste that in there. Okay, so that's it. Okay, and that makes sense. Yeah, 21.84%. Okay, last one. What percent of easy Sudoku puzzles take Mrs. Starnes between 6 and 8 minutes to complete? Okay, so if we're going to do our little quick graph. Okay, there's the mean, and they say between 6 and 8. Between 6 and maybe 8's over there. We want all that area there. Okay, so we'll do normal CDF again, and then just keep 6 as our lower like it was before, but make our upper 8. And it really shouldn't change that much. The only difference is there's just not this area here, but that's so little area that, yeah, look at almost exactly the same. So okay, so part C was 21.70%. 21.70%. Okay, so let's do the same things with table A. So we'll just have to find z-scores for all these first. Okay, so here for part A, let's do that. Okay, so part A was the proportion less than 3 minutes. So we'll first find the z-score associated with 3. Okay, so that's negative 2.3, 0.9. Okay, this will be negative 2.5, we'll say 6. Okay, so now this is I think this is the first z-score that we had to round, so that means we're not going to get the same as we got when we did it with the calculator. Okay, so let's look at the z-score over here. Negative 2.56. Okay, there's negative 2.5 there. 0.06. So it's that value there. Okay, so from that we got 0.52%. Okay, what did we get before? Yeah, 0.53. Okay. Okay, for part B, oops. Okay, part B was between 6 and 8 minutes, or more than 6 minutes. So let's find the z-score associated with 6. That value. Okay, so that's 0.78, let's say. Okay, so let's find the value associated with that z-score. 0.78. 0.7, there's 0.08. So right there. So, and we want the values that are more than 6, so that proportion is less than, so we'll have to do 1 minus. So 1 minus 0.7823, 0.2177, it's 21.77%. Before. Yeah, 21.70%. Yeah, so now they're off by a little more because we had to round the z-scores. Okay, so last one. We've already found the z-score for 6. Next one we want to find between 6 and 8. So now we just have to find the z-score for 8. Okay, and then we could even use the empirical rule for this. Less than 3 standard deviations from the mean, more than 3 standard deviations above the mean is 0.15%. But let's look at table A just to see, maybe it's off by a little. So 3 standard deviations. Oh, it's here. Here's 3 and there's 00, so that's it there. Okay, so now the value associated with 6 standard deviation, or for the value of 6 was the proportion less than was 0.788, and then this one here, I'll write that down. This percent was 90 point. Let's just do the proportion first. 0.9987. So now we're going to subtract this. Whoops. We'll subtract this value with like this value that we got from the chart for 0.6. So let's do that. So 0.9. Oops. 0.9987 minus 0.78. Anytime you want to find in between two, just subtract the percents that you find for each one. Okay, so let's do that. 0.9978 minus 0.7823 is 0.2155, so 21.55%. Okay, so that's using table A. What do we have before? 21.70%. Oh, actually, sorry, this one, 21.77 was for B. So that one's up pretty far off. Not too far off considering it's a percent. 0.07. It's really 7/1000s. So it's still pretty close. Okay, and then this one was like 15/1000ths away from the one that we got in the calculator. So pretty close still. Okay, next one, 63. Okay, so they say refer to the same exercise. So find the 20th percentile of Mrs. Starnes' Sudoku times for easy puzzles. Okay, so now we're given the percent. Anytime you're given the percent or the proportion, we'll go the other way. And so this will be the first problem that you have to do inverse norm in the calculator or going backwards with table A. Okay, so on the calculator, here, let's look. So anytime you're given a percent or a proportion, we'll do the same thing, but do inverse norm. So the area less, actually, let's do that first. If we're doing a normal graph, okay, this is, this would be 50%. Anything to the left or right of the mean is 50%. So the 20th percentile might be somewhere around there. That value is what we're looking for, where this area here is 0.2. 20% is to the left. That's the 20th percentile. 20% of the data is less than or equal to whatever value. So inverse norm finds this value. So think about normal CDF, you're given this value and you're finding the area. Inverse norm, you're given the area and you're finding the value that's at that. That will give that area. Okay, so let's go back. So 0.2 is the area. Okay, so that's the z-score associated with that. So here, so now that we've got the z-score, we'll do negative 0.8416 equals x minus the mean. The mean was 5.3. All over standard deviation was 0.9. So notice the first thing we'll do is, so now we have to take this equation. We found the z-score with the inverse norm, and then we'll solve for this x value. Okay, so we'll times both sides by 0.9. Cancel those out, and times this by 0.9. Okay, so that'll be what we do in the calculator there, times by 0.9. Okay, and then now we have negative 0.75746, and then we have to, that equals x minus 5.3, and then we just add 5.3 to both sides. Okay, so that's it. So that's the x value. So 4.54. Okay, so that's the value that's at the 20th percentile. Okay, if we were going to do it the table A way, 20th percentile, these are kind of naturally kind of percentiles. When you think about percentile as the percent less than or equal to, that's really what these values are. And so just look in here, kind of scan until you get the closest number to 0.2. It's like maybe this one here. Okay, so 0.2005, and then now look at the z-score associated with that. So notice that's negative 0.84. Okay, and think about it, that's almost the exact same z-score that we got from the calculator. Okay. All right, and we'll do the same thing. Make an equation. Okay, and then we'll just do it all in the calculator. Times by 0.9. Oh, I didn't do that. Record this earlier. Okay, so I'll do that here. 0.84. Oops. Okay, times 0.9. That's negative 7 point negative 0.756. Okay, and then add 5.3 to both sides, and you get 4.544. Okay, so same thing really. Okay. Okay, actually I just realized I could have done when I set up inverse norm, I use 0 and 1 for the mean and standard deviation. And remember, anytime you use 0 and 1, you're gonna get standardized scores, which are z-scores. But we could have used, I forgot, we had the mean and standard deviation for this, 5.3 and 0.9. If we had put that in there, that would have given us the actual value without having to do the math. Okay, but that's okay, so it's good practice. Okay, so for 65, they talk about something called deciles. So, quartiles are split up the distributions into chunks of 25%. And so deciles split it up into chunks of 10%. So deciles of any distribution are the values at the 10th, 20th, so on up until the 90th percentiles. The first and last deciles are the 10th and 90th percentiles respectively. And what are the first and last deciles in the standard normal distribution? Okay, so we're in the standard normal distribution. We're looking for z-scores. Okay, so let's go to the calculator. So first off, the fact that we're given deciles, we're given percentiles, means we're going to do inverse norm. And the fact that we're doing finding standard norm, values for the standard normal distribution means values for the standard normal distribution are z-scores. And so we'll use 0 and 1 as the mean and standard deviation. Okay, we'll do these different ways. So that so certain people's calculators, have this left, center, right. When we do table A, it's assumed it's to the left, and so we'll if it's not, if it's to the right, then we have to subtract. Here, so let's keep going. Okay, so the 10th percentile, 0.1, that's to the left naturally, and that's it. Okay, so the z-score associated with the 10th percentile. So if we were looking at like a graph, okay, this is 0 and 1, and then this is 0. And so the 10th percentile will be kind of whatever value down here. We'll create an area of 0.1 to the left. So maybe right there, whatever that is, here. And then that area is 0.1 for the 10th decile. And so we found in the calculator that value down there, that z-score, is negative 1.28. Okay, so the 10th decile, or the first decile is, for the standard normal curve, is negative 1.28. Okay, let's look for the last decile, ninth one. Okay, so we want 0.9%. Actually, let's do that let's draw that first. So, actually, let me do this first. Okay, we want 90% to be less than or equal to that value, so maybe somewhere around there is the that all this area is 0.9. Okay, so that's the value. Whatever value is right here, whatever z-score is right here, that's the z-score we're looking for. Okay, so let's do that. Oh, and if your calculator doesn't have this option of left, center, right, it's really implied that it's just left. It's always left. Oh, so I'll show you doing 0.1 to the right. So if you do 0.1 to the right, so notice if there's 0.9 to the left, then there's 0.1 to the right. And so that's another way of doing it. So that's this value, positive point, or positive 1.28. And I think I did another way. You know, I recorded these calculators earlier. We could do it another way. We could also do 0.9 to the left. I think I did that. So inverse norm. And then, yeah, 0.9 to the left, same thing. We should get the same answer as before. Yeah, okay. Okay, so let's do the table A way of doing it. So, so if we're looking for the first decile, that's 10% less. So we'll look for 0.1, kind of scan around in the inside until you see the closest number to 0.1. That looks like it's this value here. Okay, so that's a z-score of negative 1.28, and that's what we got before. Okay, and then the 90th, or the 9th decile would be 0.9, looking for 0.9. Looks like that value is closest to 0.9, and that's 1.28, like we'd expect, like we got before. Okay, so either way, just as good. Okay, next one, IQ test scores. So scores on the Wechsler Adult Intelligence Scale and IQ test for the 20 to 34-year-old age group are approximately normally distributed with the mean 110 and the standard deviation 25. Okay, what percent of people aged 20 to 34 have IQs between 125 and 150? Okay, the fact that they're asking for percent means that we're going to do normal CDF. So here, let's draw our picture first. Okay, and I should have been labeling it this way. Normal with the mean of 110 and a standard deviation of 25. Okay, and we want the percent that are between 125 and 150. So it might be like around right there is 125. And maybe right there. Maybe a little way. Maybe right there is 150. Okay, so that's the error that we're looking for our answer. Okay, so we'll do normal CDF. Whoops. And we'll look at values in between. Okay, yeah, so 125 will be our lower and 150 will be the upper. And then we'll put in our mean and standard deviation. So for A, we'll say 21.95%. Okay, for part B, they say Mensa is an elite organization that admits as members people who score in the top 2% on IQ tests. Okay, what score on the Wechsler Adult Intelligence Scale would an individual aged 20 to 34 have to earn to qualify for the Mensa membership? Okay, so the fact that now we're looking for a value in context, right? A score on the test is like a value. We're not looking for percents or proportions anymore. We're looking for values. And so that's going to be inverse norm. Okay, so let's do that in the calculator. Okay, so second vars, distribution, number 3. Okay, and we want the, here, let's actually draw a picture first. So for B, picture, oops. Okay, we want the top 2%. What score is going to give us the top 2%? So we want some score way over to the right, some score, so that the area to the right, all this area is 0.02, top 2%. Okay, so that means we could do 2 ways. We could find, that means the area to the left, everything to the left here, is 0.98. So we could do area to the left of 0.98, or we could do inverse norm and do to the right and use 0.02 for the area. Okay, so it looks like I did to the left. This will be, if you don't have the option of the tail, this will be what you'll have to do, 0.98, since it's naturally to the left. All right. Okay, and that's it. So that score, to be in the top 2%, you'd have to score 161.344 on the test. Okay, so let's say we did it a different way. Let's say we did if you have this, you could just do the 0.02 to the right, and let's just make sure that we get the same thing, just so we can see that you can do it more than one way. Should get the exact same answer, which we do. Okay. Whoops. Okay, whoops. I messed that up. Okay, so let's do the table A way if we were going to do it. So if we want, table A is naturally to the left, so we have to look for the 0.98. So just look for 0.98 in here, kind of scan around 0.98, number closest. Might be this 0.9803. 0.9803. Okay, that's a z-score of 2.06. Okay, and then now we'll set up use the formula. So z equals value minus mean over standard deviation. Okay, so we'll do the z-score is 2.06 that we found just now. Okay, the value is what we're looking for. We know the mean and standard deviation. Okay, in the calculator, multiply both sides by 25. Cancel those out. So 2.06 times 25 is 51.1. Oh, 51.5. Okay, and that equals x minus 110, and then just add 110 to both sides, and you get 161.5. Okay, so pretty close. A little off from what we got in the calculator, but pretty close. Okay, for next one, number 69, they say at some fast food restaurants, customers who want a lid for their drinks get them from a large stack near the straws, napkins, and condiments. Okay, the lids are made with a small amount of flexibility, so they can be stretched across the mouth of the cup and then snugly secured. Okay, when lids are too small or too large, customers can get very frustrated, especially if they end up spilling their drinks. At one particular restaurant, large drink cups require lids with a diameter between 3.94 and 4.05 inches. 3.95 and 4.05 inches. Okay, the restaurant's lid supplier claims that the diameter of its large lids follows a normal distribution with a mean of 3.98 inches and a standard deviation of 0.02 inches. Okay, let's write that. So it's a normal distribution. The mean is 3.98 and standard deviation is 0.02 inches. These are both the same units, both inches. Okay, assume that the supplier's claim is true. Assume that that is the mean and standard deviation of the diameters of their large lids. Okay, so they say what percent of large lids are too small to fit? Okay, so they say that large drinking cup lids, or large drinking cups require lids that are with a diameter between 3.95 and 4.05. So what percent of large lids are too small to fit? So that'll be lids that have a diameter that's smaller than 3.95. So that's really what they want. So they want values of the lid that are smaller than 3.95. Those will be too small to fit. Okay, so let's find that in the calculator. Okay, we want a percent, and so we'll do normal CDF. It's too small, so we'll just a small number. That's good. It's a big negative number. Make that up to 3.95. Okay, put in the mean and the standard deviation. Okay, so that's it. So too small will be about 6.68%. Okay, so next they say for part B, what percent of large lids are too big to fit? Okay, so too big is bigger than 4.05. So we want to know when is x, one of the values bigger than 4.05. Let's go back to the calculator. Still looking for percent, so we'll still do normal CDF. Okay, so now our lower is the 4.05. Okay, upper, just a big number, just maybe a bunch of ones. Okay, and then same mean and standard deviation as before. Okay, so that this is 10 to the negative fourth. So let me write that kind of like you're used to. So that is 2.327. Let's just say 2.33, and this is times 10 to the negative fourth. Okay, so remember, if you want to change um, these decimals um, using this 10 to the whatever exponent, whatever this exponent is, just move the decimal to the right or left. If this is negative, this exponent of 10 is negative, move it to the left 4 times, or that many times, and then fill in zeros with any missing spots. Okay, so then this will really end up being 0.000233. Okay, if we change this to a percent, this will be 0.0233%. Okay, so if we were going to round that, let's say to the nearest tenth, that would actually round to 0%. So almost no lids are too big to fit, and a small percentage are too small to fit. So, okay, as they say for part C, they say compare your answers to parts A and B. Does it make sense for the lid manufacturer to try to make one of these values larger than the other? Why or why not? Okay. So thinking realistically, a lot of these answers you got to think realistically. Um, if a lid is too small, then people won't even try to use it, right? If it's too small, it'll just kind of fall into the drink maybe, or like people, it'll be obvious that it doesn't fit. If it's too big, then people might kind of put it on there thinking that okay, maybe they'll be okay, maybe it'll work, and then find out that it's too big and it falls off and it spills on them. So maybe realistically, you'd rather there be lids too small rather than too big. So maybe this is a good thing. There's a higher percentage that are too small, and not that many that are too big. So maybe that's maybe they did that on purpose. So okay, so you can just kind of write something like that. All right, so if we were going to do it the z-score way, or table A way, using z-scores. Okay, so let's find, so for part A, too small is less than 3.95. So let's find the z-score associated with that. Okay, so that value minus the standard deviation, or minus the mean over the standard deviation. Okay, so we'll look in here, negative 1.5 is this value here. Negative 1.50, so that's this value. Okay, remember these are naturally less than, and we wanted to find the percent that are smaller, and so that's just it, 6.68%. And since that wasn't rounded, that should be the exact same as what we had before. Yeah, so that's exact same. Okay, so next one, let's find the z-score associated with 4.05. Okay, so look for that z-score. So notice that z-score doesn't even show up. 3.49 is the biggest one. So really kind of that is the closest that we can get to 3.5 as a z-score, 3.49. So maybe we can think about maybe a little bit more than that, a little bit higher. But maybe that's it. Actually, that's probably it. Notice any kind of 3.4s were all the same. So I bet 3.5 there'd be another, that would be the same as 3.49. Okay, so then that's the area, that's the proportion to the left, that's less than, so we want more than. So we'll just do 1 minus that number, which is 0.0002, and that's Okay, I know we got a small number last time. Is that what we got? Yeah, 0.0233. Okay. Okay, so that makes sense. Okay, next one, flight time. So an airline flies the same route at the same time each day. Okay, the flight times vary according to a normal distribution with unknown mean and standard deviation. Okay, on 15% of the days, the flight takes more than an hour, and on 3% of the days, the flight takes 75 minutes or more. Use this information to determine the mean and standard deviation of the flight time distributions. Okay, so we can one thing we can use any units we want. You know, this is in minutes and this is in hours, but they have to be the same units. So we could change both to hours or both to minutes. I'm going to change both to minutes just so we don't have decimals. So yeah, so we'll use 60 minutes instead of an hour for that one. Okay, so think about for the first, let me highlight this. So they say on 15% of the days, the flight takes more than an hour. Okay, so so let's find, so we want to know kind of, we're looking at a situation where, we don't know the mean or standard deviation, but let's say we do. We know it's a normal curve. Okay, and whatever the mean is, we don't know what the mean is. Okay, but we're looking at some value so that, actually we know the value is 60 minutes. And 60 minutes, and that means we want 60 is going to be somewhere around there, so that the area is 0.15, 15% less. Okay, and then for the other part, they say on 3% of the days, the flights last 75 minutes or more. So if we did a little curve for that. Okay, don't know the mean. Okay, but on just 3% of the days, so pretty far over to the right, so that this area here is 0.03. Okay, and then that's 75. Okay, so we know the mean is somewhere in between 75 and 60. If I had to guess, I'd say it's closer to 60, so maybe around 65 or 67 or something, 68. So let's see. And then if we had to guess the standard deviation, probably 7. If this is 67, this is like 1 standard deviation, because there's 15% less than 1 standard deviation, so, or 16%. So okay, so just for practice, kind of thinking about how this works. Okay, so let's just use let's just use table A for this one. So here, let me grab table A real quick. Okay, so let's find the z-score. Whoops. Let's first find the z-score associated with 0.15 to the left. Oh, whoops. Here, sorry, let me... Oh, I got the wrong... Whoops. Okay, there we go. Okay, so yeah, let's first find the z-score associated with 0.15 to the left. So let's scan in the inside for 0.15, 0.15, somewhere in between those two. So notice, like, this is like negative 1.03, and this is negative 1.04. Actually, let's just pick negative 1.04. Okay, so the z-score for this one would be negative 1.04. Okay, that means we can make an equation. Negative 1.04, that's the z-score, is the value. We know this value was 60 minutes, minus the mean, which we don't know, over the standard deviation. Okay, let's do the same thing for this one. But remember, the inside is area to the left. So if 0.03 is to the right, that means all this area to the left is 0.97. So 0.97 is what we're looking for inside here. So 0.97. Oh, whoops. Here, I got the wrong one again. Here, let me get the right one. Okay, so let's scan for 0.97. Oops. So, okay, it looks like that for sure. 0.9699. Okay, that's 1.88. Okay, so let's do that. So the z-score for that one, what was it? 1.88. Okay, so let's do our formula for that one. So 1.88 equals, okay, the value was 75 minutes. Okay, mean we don't know, standard deviation we don't know. Okay, so think about, this is what we have. So now think about, back to Algebra 2. I think maybe even Algebra 1 and Pre-Cal they did this. So think about, you have two equations here and two unknowns. And so we'll solve this as a system of equations. Okay, a bunch of ways to do this. I'll show you which way I think is best. So first off, like a little algebra trick. If you ever want to solve for the denominator in a fraction, get the denominator by itself, you can always switch it with whatever the fraction equals. So this whole fraction equals this thing, so we can switch this thing and then this denominator. So we'll just switch these two. So we'll get standard deviation. Okay, so we got standard deviation solved. And then we'll do the same thing over here. Switch those, so that's something you can do in math. And then now we have expressions that both equal the standard deviation, so we can set them equal to each other. So let's do that. So we can do 60 minus mu over negative 1.04 equals 75 over mu minus mu. Okay, now we have an equation with one variable, so now we can solve it for the mean. Okay, anytime you have two fractions equal to each other, you can always cross multiply. So we'll do this times this equals this times that. Okay, we can do different things. Maybe we'll just distribute though. Okay, so first do 1.88 times 60. And then negative 1.04 times 75. That's 78, negative 78. Okay, we will, we can do different things. I'll add this to both sides. And then maybe at the same time, I'll add 78 to both sides. Okay, so those cancel and those cancel. Okay, if we add the left-hand side, it becomes 190.8. And then right hand side is 1.92 times mu, and then just do 190.8 divided by 1.92. Okay, and then that means the mean. Wait, did I do that wrong? Okay, sorry, I just noted I made a mistake. That number shouldn't have been that high. So I realized, here, let me fix this. I can kind of fix it quickly. It was more than, I don't know if people noticed while I was doing it. It was more than 15%. On 15% days, the flight takes more than an hour. I don't know why I was doing less than. Okay, so this is a mistake. It shouldn't have been more than here. I mean, it shouldn't have been less than. Okay, it should have been more than. Okay, so the 60 was somewhere, should have been somewhere over here. And this was 0.15. Okay, so let's fix that. Okay, we would have gotten the same value. So just know, anytime you get like, you know, if we got a z-score that was represented 15% to the left, and that was a negative one. If you want 15% to the right, 0.15 to the right, it's going to be the same z-score but positive. And the reason is because these are symmetric. You know, if you have the same area, if you're looking at the kind of the same area on both sides, they're going to be associated with the same z-scores, but just this one will be negative and this one will be positive. So really just this z-score should have been positive. So let me change all those real quick. Whoops. Okay, so that actually won't be too bad. Fixing that. It'll be positive, 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 positive. Okay, and that'll make that negative. That a negative there. Okay, and then that'll change this value here to 0.84. Okay, so not too bad as far as fixing it. Wait. Is that the only mistake? Oh. And then, whoops, here, let me fix a lot of this here. So this will be, also this will be end up being a positive 78. So we'll have to subtract 78 from both sides. Let me fix that. So positive 78, and then we'll subtract 78 from both sides. Alright, so we're going to fix a lot. Okay, so that affects this value here. So 112 minus 78, we'll have to do that. Okay, so just made some mistakes. Okay, so that'll be 34.8. And then divide that, 34.8 divided by 0.84. Okay, actually that makes sense now. For some reason I forgot, forgot that this should be, so if we look back to our distributions kind of now that I fixed this, it makes sense our mean should be less than 60 and 75. So that makes sense when, when we divide those, we end up getting 41.429. And that makes sense now. Okay, sorry about that. All right, and then to find the standard deviation, we plug it back into either one of these that are solved for the standard deviation. So I'll just plug it back in here. So we'll do the standard deviation is 60 minus the mean that we found. Okay. Okay, and that ends up being 17 0.857. Okay, so next one. Okay, normal highway driving. The dot plot shows the EPA highway gas mileage estimates and miles per gallon for a random sample of 21 model year 2018 midsize cars. Okay, explain why this distribution of highway gas mileage is not approximately normal. Okay, so, not approximately normal because we can kind of tell just by looking at it. There's kind of what looks like almost for sure an outlier here. Maybe even one of these is an outlier. I don't know about that one, but let's actually that's probably good enough. If there's outliers like this is this looks like it's even skewed right a bit. So yeah, so it just looks this distribution looks skewed. We can even say skewed right. And so can't be normal at the same time. And normal distributions are symmetric, which are symmetric. Okay, so something like that. Okay, next one. Okay, refrigerators. Okay, Consumer Reports magazine collected data on the usable capacity in cubic feet of a sample of 36 side-by-side refrigerators. Okay, here are the data. Okay, these are all usable capacity of refrigerators in cubic feet. Okay, a histogram of the data and summary statistics are shown here. Is this distribution of refrigerator capacities approximately normal? Justify your answer based on the graph and then in the empirical rule. Okay. So first off, based on the graph, it looks almost normal, I think. If this wasn't there, which is just a one value, right? The frequency is just one for this. So there's one value in between 12 and 13. And even that is pretty close. That's the 12.9. Even that is pretty close to 13, and so just a little bit more, and that would have just raised this box, and it would be pretty normal. Maybe slightly skewed left, but I don't know, not even. So just on that face, it looks approximately normal. Okay, but one way to do it, when they say in the question they say based on your graph and the empirical rule. So based on the graph, looks like it could be approximately normal. So based on the empirical rule says that one thing it says is that 68% of the data should be within one standard deviation of the mean. So let's look at the mean. So the mean is 15.825. Okay, and then the standard deviation is 1.217. So let's say we do the mean. Let's look at like the mean minus one standard deviation. And then let's look at the mean plus one standard deviation. Okay, so we'll do 15.825 minus 1.217. Okay, that's 14.608. And let's do the same thing but plus. Okay. 17.042. Okay, so this is one standard deviation less than the mean, one standard deviation to the right of the mean. So that means that 68% of the data should be in between these two numbers, in between one, within one standard deviation of the mean. Okay, so let's see. So let's see how many values are in between that. And so they were nice. They put these in order. So that's good. Okay, so let's look at all the values. So greater than 14.608. Starting all these. Oops. All these at the top. Up until 17.042. So that's all of those. And then all of those. Stop there. Okay, so that's one. So there's 6 here. 18 total, 19, 20, 21, 22, 23, 24, 25. So there's 25 pieces of data that are within one standard deviation. Okay, 25 out of the 36. 25 divided by 36 is 69.4%. So that means that 69.4% are within one standard deviation of the mean. And the empirical rule says 68%. So that's pretty close. That's pretty close. Let's see. If you did 2 standard deviations, maybe we'll just go to 2. So let's do the same thing. Let's look at the mean plus 2 standard deviations, and then the mean minus 2 standard deviations. Okay. So we'll do 15.825 minus 2 times 1.712, so that's 4. Okay, that's 13.391 plus, and that's 18.259. Okay, so we want to know what percent of the data is now within 2 standard deviations. So what percent of the data is between 13.391 and 18.259. Okay, so bigger than 13.39. We now include all that data, and then even the blue data, and then less than 18. Yes, that's all that data. Okay, so that's all but 2. So that means if there's 36, that means there's 34 values. So that means 34 out of the 36, which is divided by 36 is 94.4%. And that's within 2 standard deviations. Okay, and the empirical rule says that 95% of the data, so pretty close. Okay, maybe we'll do one more. We'll do, empirical rule goes up to 3 standard deviations, even though that's probably good enough to say that this is approximately normal. Okay, so that's 12.174. Okay. The other one, 3 standard deviations. Oh, I don't know why I was doing. I'm just tired. These are both minuses. These are both pluses. Okay, so that's 19.476. Okay, and we can see 100% of the data is in between that because now that gets those last two values. Yeah, so now all those values. Okay, so 100% are within 3 standard deviations. So 100% within 3 standard deviations. And the empirical rule says 99.7. So, so basically all the data should be within 3 standard deviations, or almost all. So that makes sense. So just based on that, based on doing that math, we can say this is approximately normal for sure. So, okay, so 83. Use your calculator to make a normal probability plot. Okay, and sketch this graph on your paper. Okay, I'm going to leave that. That's in the answer key. So I'm going to leave that for people to look in the answer key. Actually, hold on. Okay, so I'm going to make this the last problem. I think the rest of the problems, the answer key is pretty good to answer those questions, and none of the rest of the problems need a calculator or table A or anything. So I think the answer keys are pretty good. So I'm going to make this the last problem for this video. But let's do 83. They say this is something new. They say use your calculator to make a normal probability plot of the data, and then sketch this graph on your paper. Okay, so to make a normal probability plot, we want to use the z-scores on the y-axis. So we want to convert all those, all the values that are in like that table up there. We're going to convert all those to z-scores, and then we're going to plot those values, and then the z-score on the x-axis. We'll use like all these values in the chart will be on the x-axis, and then their corresponding z-scores will be on the y-axis. So let's do that first. So if we look here, so first we'll just enter all that data in. And so I did that already. So remember, if you go to stat and then edit, you can enter in. So there's all that data in there. So there's 36 values in there. So think about first thing we want to do to, we did this before in class. We want to convert all those values to z-scores. So remember, the first thing to do is subtract the mean from every value. And so the way to do that is to go to L2, go over to L2, highlight L2, and then hit enter. And then remember, we want to take all those values from L1, so do second one, L1, and then subtract the mean. So that mean was 15.825, I think. Okay, so that'll give us those new values, right, with the mean subtracted. And then we want to also divide those. So the new mean of that L2 is 0, just like we want for standardized scores. Okay, but now we want to change the standard deviation, and we'll do that by dividing each of those pieces of data in L2. We'll divide those by the standard deviation. Let's do that now. Highlight L3, hit enter, and then now we want to do L2 divided by the standard deviation. So these are now L3 is going to be all z-scores. Okay, and those kind of look like z-scores. Negative 2.4s, pretty far from the mean. Okay, and then now we're going to plot those. So if we go to second stat plot, second y equals, so which is stat plot, and then we want to turn that on, or hit enter, turn it on, and then it's already a dot. We wanted a dot plot, and that's already a dot plot. That first one, that's already highlighted. But we want our x list to be L1, which is all the values, the actual values, the usable capacity of the fridge. So that'll be L1. But we want our y list to be all the z-scores, which were L3. So we'll just change those to L3. Okay, and then remember to graph. So everything else looks good. Remember to graph, do zoom stat, which is 9. Zoom 9. And here I'll get rid of that line up there. Okay, so look at that. So notice that graph is almost exactly linear, and that means that the data is roughly normal. Okay, so yeah, so it's just something a little new. So they say, use your calculator to make a normal probability plot. So that's what we did. Sketch this on your graph. So what does this graph, so part B says, what does this graph in part A imply about whether the distribution of refrigerator capacity is approximately normal? So it is approximately normal because the normal probability plot is roughly linear, in this case almost exactly linear. Okay, so that's the last problem. This video is already way too long, I think. So that's the last problem I'm going to do. Yeah, I think the answer key is pretty good for the rest of them. Yeah, so that's it for this.